Exam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at Cape Chemistry Unit 2, 2022, Module 2, Analytical Methods and Separation Techniques. Let's go. So this is Module 2, and we're looking at question 2. Mass spectrometry is a process by which the atomic mass of atoms or molecules is determined. Explain how a mass spectrometer works to obtain a mass spectrum of a molecule. Let's start with the steps. 1. After a vaporized sample is injected, it is ionized by bombarding it with electrons. 2. The positive ions move into the accelerating chamber, where an electric field accelerates positive ions towards a magnetic field. 3. The fast-moving ions are deflected according to their mass and charge as they pass through the magnetic field. Lighter ions are deflected more than ions with a larger mass-to-charge ratio. 4. The ions are detected by an instrument which is attached to an amplifier and a recorder. Now, the steps we just went through can be seen on this diagram. Here we have the vaporized sample being injected, and the electric gun will cause electrons to bombard the atoms where they'll become ions. They will then enter the acceleration chamber, where a negatively charged plate will attract the positively charged ions to travel at the same speed. They will then enter the electromagnetic chamber, where they will separate based on their mass to charge ratio. The lighter ions will be more deflected than the heavier ones. They will then hit the detection plate, where it will be amplified and recorded as lines. Here's an example of what is taking place in the mass spectrometer. In this case, we're looking at a molecule that will be bombarded by electrons from the electron gun. The electron from the electron gun will remove an electron from the molecule, forming the molecular ion or the parent ion. Now, this process is called ionization. After ionization, we're going to have fragmentation. When the parent ion or the molecular ion splits, it's called fragmentation. And we now have a fragment ion and a radical. The fragment ion is what will be detected by the mass spectrometer, not the radical. So here we have ethanol. So the gaseous molecule will be placed in the mass spectrometer, where it will form the molecular ion through ionization. It will then be fragmented. Now, it can be fragmented in various ways. It can be fragmented here, where this side can become the positive ion or the fragment ion, and the OH can be now the radical. The machine cannot identify the radical because it is not charged. However, it can identify this part of the molecule, which is the fragment ion, and it will give you a reading in the form of lines for this fragment ion. So you can count 12 and 12, that is 24, 25, 26, 27, 28, and 29. So on the mass spectrometer at the MZ section at 29, you can have a peak. Now, if it splits here, now this part can be the fragment ion, which is at 15. So this could be 15 right here. Now, if the 15 fragment ion is the highest peak, then it becomes the most abundant peak. And the most abundant peak is the stable peak. And so if this is a fragment ion, then everything on the right-hand side will become the free radical, and the machine cannot identify the free radical. So if you're looking at the two examples, where we remove or we form this fragment ion and the free radical. We could also form the fragment ion being OH plus and the C2H5 becoming the radical. And the machine will not be able to identify the free radical, but only the fragment ion. So this is 16 for oxygen and 1 for H, which will give us a peak at 17. So this could be the 17 peak, OH plus. So just remember that any peak that is identified on the mass spec, it is positively charged. To part B. Figure 3 shows the mass spectrum of a haloalkane. Now, if you look at the spectrum, you can see the various lines. We have a line at 15, we have one at 27, we have one at 39, 41, and here we have 81, 107, one at 122, and of course, this is at 124. So this is the mass spectrum of the haloalkane or a halogenoalkane. Part 1, state the MZ ratio of the M plus and the M plus 2 peak. In this case, we have two isotopes of bromine that are close in number. So one is at 79 and the other is at 81. So you see that the isotope for bromine at 81 is 2 units higher than bromine 79. So the 2 units higher will be the M plus 2 peak. And the M plus peak, which is the molecular ion peak, is at 122. So your answer is M plus is equal to 122 and M plus 2 is equal to 124. So this particular molecule that is breaking up, that is being fragmented, has bromine 79 and another isotope can have bromine 81. So if you look at part 2, deduce the formula of the fragments at MZ ratio 43, 107, and 109. So what we do first, because you can't remember, they did not tell us what molecule we're looking at. They simply said that it showed the spectrum of a haloalkane, but we have the M plus peak to go with as a guide. Now, if you use trial and error, and you should start with 2 carbons, 1 carbon, 2 carbon, and then your bromine, and you could call this bromine 79, and these are H's. Now, if you look at this section here, if you count the number of carbons and H's, 2 carbons and 5 H's, you'll end up with this being 29. And 29 plus 79 is equal to 108. All right? So right away, we realize that 108 is way short of 122. So you could step it up and put another carbon there. Add back your Br 79. Now we're going to add up all of this and add it to this to see if we get 122 to identify the type of haloalkane that we have. So 3 times 12, 36 plus 7. So this section is 43 right here. And if you add 79, you get 122. So this becomes our M plus peak, which is the parent ion or the molecular ion peak. So all we do for 124, we use the same Br, but we're going to change the type of bromine. So this time, instead of bromine 79, we use bromine 81. So if you add 43 plus 81, you end up with 124. So in order for us to deduce the formula of the fragments, we have to start with our molecular ion, which is CH3, CH2, CH2, Br, bromine 79. So CH3, CH2, CH2, Br 79. And we're going to fragment this particular molecular ion to form CH3, CH2, CH2. And this will give us our positively charged ion at 43. So this can be identified because it is positively charged at 43. Now the Br is the radical that the machine cannot identify because it is not positively charged. So we identified the 43. Let's see how we can identify the 107. If you should take the same molecule, which is CH3, CH2, CH2, Br 79, but this time we're taking the same molecule with the parent ion, so this of course should be positively charged. And if we fragment it at this point, we now have 15 as our radical, and this entire part here, which is from here to here, would be 28 plus 79, which give us 107. So this would be the fragment ion that will give us the line at 107. So we have CH2, Br 79 for the 107 peak or fragment ion. And then now for the peak at 109, you realize it is 2 units higher than the 107. So we use the same fragment ion. However, this time we change the isotope from 79 to 81. And so we have CH2, Br, but this time right here would be 81. And we identified 43, 107, and 109. Now I'm showing you that there are other possible answers. Now you could form this fragment ion at 43, where we have CH3, CH3 positively charged. And we could form this particular fragment ion where we have CH3, Br 79, CH3. And of course, the same thing could be used for 109, but this time we would change the 79 isotope to 81. So these are other possible answers for the same question before. So of course, this would be your 2-bromopropane if they ask for the name in this case. And this, of course, would be a secondary haloalkane. So now for 2B part 3, they're asking us to determine the formula of the M plus peak and the M plus 2 peak molecular ion species and name the haloalkanes. So we already identified what those peaks were for the M plus 1 and the M plus 2 peak. Let's look back at that. So you can see here at 122 would be the M plus peak, and that is your molecular ion peak, and the M plus 2 peak would be 2 units higher than the M plus peak. And we identified that that would be at 122 would be CH3, CH2, Br 79. All right. And for it to be M plus 2 now, we just simply use the bromine 81 instead of bromine 89, and we get our 124. So that is our molecular ion, M plus, CH3, CH2, CH2Br with isotope 79, and it must be positively charged. And for the M plus 2 peak, the same formula, but this time we use Br isotope 81. And of course, they ask for the name of the haloalkane, and this would be 1-bromopropane, because we have the Br on the first carbon, so 1-bromo, and we have 3 carbons, hence propane. So the full name is 1-bromopropane. So 1 mark for the M plus peak, 1 mark for the M plus 2 peak, and 1 mark for the name. 2 part D. At the end of an organic reaction, a TLC of the reaction mixture indicates the presence of unreacted starting material, benzoic acid, as well as the impurity 1,4-dimethoxybenzene. Part 1. Outline a series of steps indicating how this mixture can be separated and the 2 components recovered by the process of solvent extraction. So 1. Dissolve the mixture in an organic solvent, example, diethyl ether or dichloromethane, to serve as the organic layer in the extraction process. Remember, you have 2 layers, an organic layer and an aqueous layer. 2. Add an aqueous-based solution, example, sodium hydroxide or sodium bicarbonate, to the solution. Benzoic acid will react with the base to form an ionic salt, which is soluble in water, therefore moving it to the aqueous phase, leaving 1,4-dimethoxybenzene in the organic phase. Part 3. Separate the aqueous layer from the organic layer using a separating funnel. 4. Recover benzoic acid by adding a strong acid, example, hydrochloric acid. This will convert the salt back to benzoic acid, which will precipitate out. Then you can filter. Part 5. Recover the 1,4-dimethoxybenzene by evaporation. And those are the steps you would take. Part 2. State what is meant by the term partition coefficient. Now, partition coefficient, K, is a constant of the solute concentration in each solvent at equilibrium. So once you shake the separating funnel, the 2 phases will now be in equilibrium. So here we have an example. In this case, we're moving the solute from an aqueous phase to the organic phase. And if that's the case, when we write the expression for K, we must go with the product over the reactant. So this is just an example. If it was the other way around, if we are moving the solute from the organic phase to the aqueous phase, then the aqueous phase would be on top, because it must be product over reactant. So let's look at an example. If I have a funnel and we have our phases, one here and the other here. So let's call this here the organic phase. And this here would be the aqueous phase. If equilibrium is established, then you won't be able to see the 2 phases. What you'll see is a mixture at equilibrium. And this is what we mean by the partition coefficient is a constant of the solute concentration in each solvent at equilibrium. So if the solute, let's call this, let's put a different color. If the solutes were here and you want to put it here, when you shake and it settles, once it settles, you would now have the phases again separating. That's the organic phase. And this here was the aqueous phase. And of course, we'll have some of the solute being transferred to this aqueous phase. Some might be left back. And of course, you might have to do another extraction to remove the rest. But this is just an example to show you what is going on. So this is what is taking place for the steps and for the definition of the partition coefficient. D part 3. If iodine is shaken with 100 cm³ of water and 100 cm³ of an organic solvent, the concentration of iodine in the water layer is 4.0 times 10 to the minus 3 moles per dm cube, and in the organic solvent, it is 1.0 times 10 to the minus 2 moles per dm cube. Calculate the partition coefficient for iodine between the organic solvent and water. Now, based on this question, you'll see that the higher concentration is in the organic layer. So if it is already shaken, then it means that iodine moved from one layer to another layer. So in this case, the higher concentration would be the one where the solute, or the iodine in this case, moved into. And the smaller one is where it is coming from. So if you see here they have 4.0 times 10 to the minus 3 in the aqueous layer. So that is saying that that is where it is coming from, and it is going into the organic layer or the organic solvent, which is the higher concentration. So you're going from aqueous to organic. So this is water here, and it is moving from the water to the organic solvent. And if that is the case, the equation must be X aqueous, reversible arrow, to X organic. So the iodine is moving from the aqueous layer into the organic layer. So the organic layer is the product and the aqueous layer is the reactant. And so when you write the equation for the coefficient K, K is equal to the organic layer over the aqueous layer. And in this case, we just plug the values in and we find out what K is. Now we know what K is, we can move to part 4. The aqueous layer is separated and shaken with 50 cm³ of pure organic solvent. Determine the concentration of iodine in the organic solvent at equilibrium in moles per dm cube. So this time, they're asking us to now use fresh sample of the organic layer. And we're going to now shake to establish equilibrium and then leave to settle. Once that happens, we can now find out the concentration that moved from the aqueous layer into the organic layer. Now, remember that we had 4.0 times 10 to the minus 3 in the aqueous layer. And we want to find out if that amount is in the aqueous layer, and we shake now with 50 cm³ of organic solvent, how much will be removed from the aqueous layer into the organic solvent? And remember again that we already found K. K is equal to 2.5. So now we're going to write a simple statement. Let X be equal to the concentration of iodine extracted. This is the iodine extracted into the 50 cm³. And of course, 4.0 times 10 to the minus 3 minus X is equal to the concentration of iodine remaining in the water. Because if you remove a certain amount of iodine, then what is left back is what did not transfer from the aqueous layer to the organic layer. So again, we can start with our equation, K equal organic over aqueous, which is converted into X over 50, all divided by 4 times 10 to the minus 3 minus X over 100. So we are going to remove some iodine from this 100 into the 50 cm cube. You could draw about the same diagram, but this time it would be 100 here, aqueous, but 50 in this case for part 4. And everything is equal to 2.5. So we're going to simplify this now. So let's do some math. So in this case, x over 50 divided by 4 times 10 to the minus 3 minus x over 100. And here we have it here. And here you can see it laid out. X over 50 divided by 4 times 10 to the minus 3 minus x over 100 equal 2.5. We simplify this by saying 50 into itself goes 1 time. 50 into 100 goes 2 times. So now we have 2x. 2x over 4 times 10 to the minus 3 minus x equal 2.5. So 2x equal 2.5 times 4 times 10 to the minus 3 minus x. And then we say 2x is equal to 2.5 times 4 times 10 to the minus 3 equal 0.01 minus 2.5x. Then we put the x values on the same side. So it is negative here. Once I bring it over, it becomes positive. So it's 2x plus 2.5x equal 0.01. 2x plus 2.5x equal 4.5x equals 0.01. And now we can divide by 4.5. So x is equal to 0.01 divided by 4.5. X is equal to 2.22 times 10 to the minus 3 moles per dm cube, or capital M, which means molar. So the concentration of I2 in the organic solvent is 2.22 times 10 to the minus 3 moles per dm cube. This is the end of Module 2 for 2022. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.